Hi, in this video I'm going to present you an optimization algorithm that is a very good alternative for solving optimization problems that are very time consuming to evaluate. The name of the algorithm is surrogate-based optimization algorithm. So these are the input parameters. How this algorithm works is very simple. It just equivalenting our time-consuming objective function with a polynomial function of a certain degree, which is very easy and very fast to evaluate. Therefore, the advantage is that it uses few evaluation of the time-consuming objective function, and instead evaluates the polynomial function very fast using very powerful algorithms such as Levenberg-Marquardt algorithm. For example, if we make a comparison, for instance, if you have a problem that it takes 10 minutes to evaluate, uh, and if we are using genetic algorithms or particle sum optimization, uh, to solve this problem, the user needs about, let's say, 100 individuals with 100 generation, meaning that we must evaluate the time-consuming function 10,000 times. So 10,000 multiplied with 10 minutes. So this is the runtime of the algorithm. Instead, for the same results, we can use this algorithm, and we can use, for instance, 5 samples with 10 iterations. Yes, meaning that the time-consuming objective function is going to be evaluated 15 times. That's it, and the results of the algorithm are about the same as in the case of genetic algorithm and particle sum optimization, but the running time is much smaller. Further, let's see how this algorithm works in detail. So for this, we are going to evaluate the sphere function. We are going to presume that the sphere function is going to be our time-consuming test function. Okay, so we have the sphere function here. This is the equation of the sphere function. Here we have three dimensions. Here we have the view of the function in 3 dimensions, but seen from above. Yes. So in the middle should be the lowest point. Yes, of 0. Yeah. So this is what we are aiming for. So f of 0 should be equal with 0, or a value around this. Yes. Okay. Okay. So by choosing here 1, meaning that the test function is going to be selected as the sphere function from our list of test functions, we're going to use at the beginning a dimension of 1. Yes, dimension of 1 for the input parameters, but along with f of that variable, yes, we are going to have 2 dimensions, yes, for our problem. The variable should be expressed in OX, and f of that variable is going to be expressed in OY. Okay, the lower and the upper bound is going to be -5 with 5. And the degree of the polynomial which our function will be equivalent to is going to be 2 in this case. Okay, and of course we have here a penalty coefficient because the Levenberg-Marquardt algorithm have the tendency to converge beyond the lower and the upper bound. So for this, we are going to penalize our objective function every time when the variables go out of the bound. Okay, and n samples of 5 and iteration of 10. Okay, let's see what this means. Let's execute the script. Okay, let's go to the beginning. As I said, n samples 5. Yes, at the beginning, the algorithm randomly creates 5 samples. and evaluates them. So our time-consuming test function, the sphere function, is going to be evaluated 5 times around these random points. After this step, then it's going to go in the main loop, in the iteration loop, in which every time the polynomial regression algorithm is going to be run in order to evaluate those 5 samples with a polynomial function of degree 2 in this case. Yes, so we should have 3 coefficients here. As you can see, is 0, minus 0.00 something, and 1, meaning that it's a almost perfect quadratic function. Yes, the red spline is actually our polynomial function. Yes. So we should have here in the plot, we should have 15 points. Yeah, because it runs 5 samples and 10 iterations, meaning 15 points. 1, 2, 3, 4, 5, 6. But we have here more points because the algorithm converged toward this optimal point. So our around this point, let's see. Okay, so there are the points. Yeah. Okay. After determining the coefficients of the polynomial function, the Levenberg-Marquardt algorithm, it is used to optimize that polynomial function. Levenberg-Marquardt algorithm, it is using the Jacobian and the Hessian matrix. Yes, as you can see, at a random value of 20.62, it converged to 0.00000074. Yes. Therefore, the optimal solution of the surrogate function is going to be this, which is this one of the last iteration of the Levenberg-Marquardt. Yes, and the surrogate function value of the optimal point is going to be this one, it corresponding f of x. And then the true objective function value, it is computed at the surrogate optimal point. So we are going to evaluate our time-consuming sphere function, yes, around this optimal point, and we should obtain the true objective function. Further, the next step is to add this point along with this value of the objective function to these 5 n samples. So these 5 samples, and now we have 6 samples. Then in iteration 2, those 6 samples are going to be equivalenting a polynomial function, so on and so forth until we are in the 10th iteration, where our polynomial function have been equated from 15 samples. Yes, and the final solution is the sample with the smallest objective value. In this case, is this one, and along with this, its corresponding value. Next, let's run the same algorithm for 2 dimensions. To the dimensions for the input parameters, and with 1 dimension of the f of those input parameters, it's going to have a 3-dimension problem. Yes, so of course I created another algorithm in which we would plot here the perspective of the perspective view of the 3 dimensions, x, y, and z. Yeah. On z is going to be the f of the variables. Yes. Okay, let's run the dimension of 2 degree. I'm going to use a degree of 4. I'm going to, in order to the plot to be more, how to put it, to look better, I'm going to use, let's say, 200 samples, just to look better, just to see it better with the 10 iterations. Yes, we are going to use the same function. So let's execute the script. Okay, as you can see, this is the perspective view of the 3 dimension. Yes, and those are all the samples, meaning 210 samples, and this with green is the minimum of the function. Yes. So I have another script here. It's called perspective, in which we are going to how do you call it? Not to revolve, to spin, yeah, around the y axis. This perspective view to have a better glimpse of what is happening here. I'm going to run the script. Okay, with a step of 100. Okay, execute the script. As you can see, the perspective view, how the volumes looks, how the function 3D function looks like, and here is the minimum determined by the algorithm. Okay, further, okay. So these are the values exactly as we should obtain: 0, 0, and 0. Yes. Now we are going to run the algorithm. Sorry, we're going to run the surrogate-based optimization algorithm for another function. Okay, let's use to Himmelblau function. Let's use the Himmelblau function. So I'm going to put here 2. We're going to let -5 and 5, but I'm going to use here 500 points just to look better. Yes. Yeah. Okay. And let's see the Himmelblau function. Let's search for it. Rosenbrock Himmelblau. Here it is. So here is this is the function seen from above. Yes, this is what we should obtain in 3D. So we have 4 global minimum, in which the function is 0. Here it is. The function is 0 in these 4 points, set of points: 3 and 2, -2.8 and 3.13, -3.77, so on and so forth. Yes. So we should obtain every time a value around these values. Okay. I hope everything is okay. Let's run the script, execute the script. So you can see this is the uh, objective function in a perspective view. So this is the lowest point. Yes, the lowest point is -2.8 with 3.13. Let's see if it is here. As you can see, it is exactly here, -2.8 with 3.13. Yes, the value of almost 0. Yeah. So we found the minimum. Okay. Now let's just to see how the function looks like. We are going to rotate it the same as we did previously. As you can see, here is the point, one of the 4 points. Okay. As a conclusion, this algorithm is very useful in studies where the objective function is very time consuming. In studies such as harmonic filter optimization, so to find the proper parameters for the tuning order and the quality factor for C-type filter. Yeah, so for this the assessment is very time consuming. So it can take half an hour, maybe 1 hour for one assessment. So imagine that we can found the proper filter parameters just by yeah, running, let's say, 10 samples with 20 iterations. So in 30 multiply with 1 hour or half an hour, yeah, it's very convenient, unlike using genetic algorithm, which as I told you, we should use many more iterations and yeah, number of generations. So it's much faster, this algorithm, for this kind of problems. Thank you.